Oh, we got 15 seconds. Probably we can start. So let's start. We'll have our second exam on Thursday of next class, and it'll be really the same exact protocol. There's really no seating assigned as charts, but if you leave a seat separation between your neighbor, then that'll be just fine. Materials allowed on the exam are any snacks you like, as long as they're not too noisy. It can be any kind of drinks you like, just make sure you open up a noisy can before the exam starts, and any kind of writing utensil type stuff. Also, it is closed notes, closed calculator, but you're, like before, welcome to have a 3x5 note card front to back. If you need a couple note cards, then they're always available. I bought 3 stacks and I've not been able to give them away for years, so have at it if you'd like some. Other questions about the exam folks would like to discuss? Okay, so the materials provided on the website are the same as before. The only update was more problems out of the book for the sample exam problems. And the way we could review is really up to the class. We could, for example, pick some hard problems out of this large document. This was one of the harder problems, problem number 2. Some of these problems go above and beyond the actual difficulty of an exam problem, and they're meant to just give us extensive practice, kind of like how people practice at high altitude, high temperatures, and then they do really good at Boston marathons if you've been training in 115-degree weather. So that's kind of the purpose of some of these problems. This set of problems, the sample exam, was the actual spring 2018 exam, and so it contains about the same length you'll see for our exam, the same kind of difficulty, and the problems will be different, but those are good problems to still look at. Any questions about these sample materials? Okay, one thing I should mention on the exam that we're about to do is that typically our exams are just over the sections that we cover. So our exam is meant to be mainly over 8.1 until 11.2, but there is one important exception, and that exception is that the rules for approximating integrals still turn out to be really, really valuable. So things that you might want to have on your note card may be, say for example, the trapezoid rule or the Simpsons rule. So those are things that you should be ready to have on either exam 2 or exam 3, just because they're useful things for approximation. Sometimes these integrals are just so nasty that it's nice to have a way to still do the evaluation, but approximately. Aside from that, it's going to be just the sections we covered. And what would you folks feel like would be a good approach? We could go over the spring 2018 exam, start to finish. We could go over particular problems on the last section, or I could just do problems on the board that are really kind of homemade problems that are reflective of their real exam problems. So what sounds helpful to folks? Option 3, this last one? Okay, let's go through these. That might be helpful for folks that have possibly already looked at these materials. You won't get too overly bored. So let's go for option 3. So these are problems. Essentially, I picked one problem, sometimes 2, from every single section that's on the exam that are meant to be representative of the real exam. Doesn't mean these are real exam problems, but it means if you feel comfortable about these, then you should be in great shape for the actual exam. But if you want to know what the entire scope of the real exam will be, you'd want to go to this. So any problem that's on this list would be the entire scope of the real exam. So I would never ask a question that's not somehow, some way on this material. But that's trouble with that is that it's very extensive. It's almost like a test bank. And this is a little bit more focused. So let's go to section 8.1. Instructions for 8.1 for this problem says to approximate the length of the curve y equals sine x, where x ranges from 0 up to pi using any rule you'd like. Let's go with Simpson's rule. With n equals 4. And essentially the way the exam is written is this might be the template for a problem, but maybe Simpson's rule could be used on the surface area problem, and this could be told to do exactly. And just using a random number generator, this will either be a Simpson's rule or a trapezoid rule. So let's start with this thing. The tricks with this are that if you go to this integral from 0 to pi sine x dx, this would be a really, really bad move because we're not approximating the right integral. So the very first thing is, if the problem says to approximate the length of a curve, I would write down immediately on the exam that the length of the curve is the definite integral from 0 to pi. We got 0 to pi from the domain of which we sketched the curve of the square root of 1 plus dy dx squared dx. So that's the integral that we need to approximate. It means we first need to do a little bit of work before we jump down to Simpson's rule. Any questions before we start? Okay, and if this was the real exam, maybe you spent a lot of time on the previous problems and weren't sure on this one. If that's all you wrote, and this was a 10-point problem, I would still consider that maybe 2 points. Since you did indicate that you know what's going on in that problem, any kind of information that you give me that you know how the problem should proceed is counted as understanding, and you should get points. I mean, that's not a lot of points, but it's something. So in other words, always put something down on an exam problem. Even if you're not sure what their approach is, you can just explain in ordinary words using paragraphs, complete sentences, what their approach should be. So if you get totally stuck, just explain to me how it should have gone, and I would consider that partial credit as well. So now let's go on and take this whole thing, starting with y prime for the dy dx, and take the derivative of sine. Derivative of sine would come out as cosine. So the next step is to add 1 and square it. So 1 plus y prime squared would be 1 plus cosine squared x. And if it was 1 minus cosine squared x, that would have been a sine squared. Sadly, I don't know very many great identities for this, so I'm just going to leave it alone, especially since the problem says we're just going for an approximation anyways. We will need to take the square root of that, so we can now say the length is the definite integral from 0 to pi of the square root of 1 plus cosine squared of x. So this is the integral that we would like to approximate. And at this stage, we can start Simpson's rule. Any questions before we start the rule? Okay, so in Simpson's rule, we have that delta x is going to be this point, pi, minus this point, 0. And watch out for double negatives, since that can cause some havoc in that evaluation. Divided by the number of subintervals, which was 4. So delta x is pi over 4 in this problem. So now we can start writing out the formula. The length is approximately equal to uppercase F's for Simpson's rule, subscript with 4 for n equals 4, which is equal to the delta x divided by 3, multiplying f at x naught. Then what would be the coefficient of the very next term after f at x naught? Right, so we go 4 f at x sub 1, then next coefficient? Yeah, so now we have a pattern of 1, 4, 2, 4, 2 until we get to the end. So 2 f at x1, or excuse me, x naught, x1, x2, counting can sometimes be hard, plus 4 f at x sub 3, and if n is equal to 4, we're ending at x sub 4. So we'll go plus, what would be the next coefficient? Correct, we just get a coefficient of 1, which is how we started. So it'd be f of x sub 4. So one problem with this kind of work is that it is pretty tedious to write it all out, and it is a timed exam. So let's also mention a shortcut that your folks are welcome to use. There is one extra step that we should do. That's the evaluation of delta x, which is pi over 4. If you write pi over 4 divided by 3, that's okay. Or you could write altogether, that's pi twelfths. Also tell me what x naught, x1 through x sub 4 is. I'll write this as f at x naught is meant to be the lower bound 0, plus f at x sub 1. How do we get to f at x sub 1 given f of 0? Exactly, yeah. We're going to add the delta x, which is pi over 4, into each new evaluation. So this would be pi over 4, and I forgot a coefficient. Don't forget to throw that in. Plus 4 f at pi over 4, plus 2 f at, add pi over 4 to this, that'd be 2 pi over 4, or pi over 2. So that was 1, 2, 3. Now sets at plus 4 f at x3. This was 2 pi over 4 before I reduced, so here I'll have 3 pi over 4. Plus, now we're doing f at x sub 4. This would be 4 pi divided by 4, which reduces to pi, but double check that must be the upper limit of integration. If it's not, then we possibly have a problem with delta x, or maybe I just added things funny. So this would be the valuation of the previous step. It's not quite complete because we also have to indicate what f actually was. Ways to do that is you could just rewrite all of this plugging 0 in, but like I said, that is a totally huge amount of writing, so we can use this as a shortcut. We'll say the length is approximately s of 4, which becomes all of this, where f of x, if you tell me what f of x is, I'll consider that full credit. I'll know that you know what f of 0, f of pi over 4, all the way to f of pi must be, if you tell me what f of x is. So what would the f of x actually be in this problem?
Isn't it just sine x?
Not quite. The f of x, if we let it be sine x, would be approximating just the integral that goes 0 to pi of sine x dx. So if that's our f of x, we would have been approximating that integral. But in this case, we're going for the length.
So your integrand, right? Your 1 plus cosine squared or root?
Yeah, exactly. So this function, I have no idea what the curve looks like. We could probably guess some features about it, but it's the actual function that's being used to make the approximation. So if you tell me that f of x is equal to the root of 1 plus cosine squared of x, then I'll take that as full credit, because then I'll know you know what f of 0 is, 4 times f of pi over 4 is, and I wouldn't make you evaluate any further anyways. That just saves a lot of writing. I mean, alternately, you can just write out on this one 4 times the root of 1 plus cosine squared at pi over 4, and you can just stop right there rather than evaluating, because it's typically not going to be something we could evaluate, unlike this case. But if you worked, looks like this, and you stopped right at that point, that would be full credit. Any questions about that? Okay, we did go further on exam 1, but that's because we were learning the Simpson's rule and the trapezoid rule, so we were putting in more details. We're only using Simpson's rule, trapezoid rule as a means for approximation, so that would be a decent stopping point on that one. And if after the exam you're really curious what the length of the curve sine x is from 0 to pi, you can do all those evaluations in the calculator using that function. But let's go on to the next one. Unless there's any questions about it. Okay, so problem number 2 takes us to section 8.2, where we're doing essentially the same thing, except we're now looking at the surface area of something that's been generated by a revolution about an axis. This problem reads, compute the exact surface area of the surface obtained by rotating the curve, which is y equals 4 minus x to the power of 2/3 to the power of 3/2, where the variable x ranges from 0 up to 8 inclusive, about the x-axis. Okay, so that's the statement of the problem. One feature the problem would have is I would provide you with a graph of that function. Let me do just a very, very rough sketch of what this graph could possibly look like. It goes from 0, so if I plug 0 there, I'd be taking the root of 4, which is 2 cubed, so 8. So it starts at height 8 at 0. And this function looks like it would be decreasing because of the negative x to the 2/3. So if I plugged 8 inside there, what would that be? Cubed over 8 is 2, squared would be 4. It looks like it ends up at exactly 0. So it must look maybe something like that. So there's our curve. And a more accurate, detailed curve would be given on the exam. So the things that would happen on this exam is, using a random number generator, it'll either be the x-axis or the y-axis. And I'm going to keep it dependent variable y, instead of the homework, which did change that up a little bit. So if we're rotating about the x-axis, we will get a curve that looks about like this. I'll draw this kind of lightly because I'm not very artistic. So that would be the bottom curve that we would get. And any point that ranges from 0 to 8, say you picked an x here, it gives us a point here, which is rotated down there. What we really need is this radius going that way. And that radius would be the dependent variable y. And if people are curious, I'll write a second diagram for what the setup would be if we rotate about the opposite axis. Let's do x-axis first. Any questions so far? Okay, so for the x-axis, this may be impossible to do, and if that's the case, it might say approximate using the trapezoid rule, and you would do this one exactly. But for this one, we're going to go for the exact surface area. First, we start with the derivative. We're really just repeating this approach from the start of the last problem. The derivative of this would first involve the derivative of the power function, power 3/2. So 3/2 comes down. The new power is the square root, so it would be a root of 4 minus x to the power of 2/3. But then we multiply by the derivative of 4 minus x to the power of 2/3 through the chain rule. So let's do that on the next step. We have y prime equals 3/2. I want to throw this out in front. Derivative of 4 goes to 0. This will produce a negative, so there's our negative. Derivative of x to the 2/3 gives us 2/3, and we subtract 3/3, so the new power on x is negative 1/3. Multiplying the root of 4 minus x to the power of 2/3. So that's the full derivative with the chain rule in 2 steps. Any questions with this format so far? Okay, so it doesn't look all that wonderful, but I guess it is what it is. There is at least a cancellation going this way to this way. So now that we have y prime is equal to negative x to the power of negative 1/3. If you prefer, you can write that as, say, x to the power of positive 1/3 in the denominator. Don't forget the negative sign, and we have 4 minus x to the power of 2/3 up above, square rooted. So then the very next step is square that derivative, add 1. So we have, maybe we should put that over here. We're running out of space pretty quickly. So let's do this in a new column. So very next step, let's just square this, going step by step. Y prime squared is going to be equal to the square of the numerator, so the negative sign resolves to positive. The root falls off, and we just get 4 minus x to the power 2/3. So that's the numerator. If we square x to the 1/3, we really just be multiplying the exponent of 1/3 by 2. So that gives us x to the power of 2/3. So that's how it stands so far. And sometimes it's hard to tell what the algebra should be on the next steps. It's hard for me to decide if I really want to divide by x to the power 2/3 or if we should leave it alone. I'll leave it alone and hope it works out. So on the next step, we'll have 1 plus y prime squared. This would be 1 plus 4 minus x to the power of 2/3 divided by x to the power of 2/3. So we can produce the least common denominator x to the power of 2/3 coming from this 1. So 1 converts to x to the power of 2/3 divided by itself, plus 4 minus x to the power of 2/3 divided by x to the power of 2/3. So that's where it stands so far. And probably a good approach with this, because there is a good amount of algebra sometimes, you do want to go a little bit slower, because if I make a mistake, say right here, that's going to be tragic, because all the algebra from thereafter changes. So I'll ask folks so far, does it look all right to this step?
I guess, why did you change the 1 to the factor, like the x to the 2/3 over x to the 2/3? Like, why did you do that?
Oh, mainly because I want to just add these two together.
Oh,
I want
okay.
this to be combined with this. And look, it's, in this case, kind of a miracle. We are going to cancel x to the power of 2/3 as well.
Okay.
But that's a really good question. Sometimes it's almost as if that's not necessarily the best approach. This time I decided just to combine the fractions and go from there. But other questions so far? Okay, so if we combine these two fractions, 1 plus the derivative squared is now equal to x to the power of 2/3 plus 4 minus x to the power of 2/3 divided by x to the power of 2/3. So lots of x to the power of 2/3. But there's a cancellation, and we get 4 divided by x to the power of 2/3. Okay, so we're getting there. The very next step, just like if we were doing the length of the curve, is to take the square root of 1 plus the derivative squared. So I write thereafter the square root of 1 plus dy dx squared, or just y prime squared if you prefer, is going to be the square root of this last step over here. So it's the root of 4 divided by x to the power of 2/3. The root of 4 goes to a 2. And if you're taking the square root of something, you're really multiplying by a power of 1/2. So you can think of the root of x to the power of 2/3 as x to the power of 2/3 to the power of 1/2. So 2/3 times 1/2 gives us just x to the power of 1/3. So finally, we're 2 x to the power 1/3 altogether. That's a lot of work on that one. Any questions so far with that problem? Okay, so probably advice I would give to this problem on a real exam is I would do this problem last. You definitely do not want to spend a half hour getting stuck in the algebra when there's other problems to show your understanding to get to. So go for the low-hanging fruit first and resolve ones like this later on. And if you get stuck somewhere in the algebra, just explain in ordinary words how it should proceed. And I would consider that evidence that you have some understanding of the method for partial credit. Well, now let's go to the formula for the surface area. The formula will be S for surface area is the definite integral as the variable x goes from 0 to 8. So that'll be our limits of integration. We take 2 pi times a radius times the square root of 1 plus dy dx squared dx. So that's our formula. I wrote it in this way because the radius that we actually pull just depends on the rotation that we made. We rotate about the x-axis, so our radius is right here. So the radius is y, but y is this entire function that we have to throw in. So we take definite integral from 0 to 8 of 2 pi times y, but y is all of 4 minus x to the power 2/3 to 3/2 times this root right here, which we worked out to be 2 divided by x to the power 1/3. So times 2 x to the power 1/3 dx. So finally, that's our definite integral. Any questions to this step? Okay, so if this was, again, a real exam, and suppose you just ran out of time, you got to this stage, I would still consider this to be most of the credit on a 10-point problem. I would say on a 10-point problem, this ought to be 8 of the 10 points, since most of the work is really just setting up that integral. And if we got stuck because maybe we made the simplest of mistakes somewhere out here, and our integral is impossible to do, that's not too unlikely, then you would still get most of the points. Maybe miss a single point for a simple mistake, and 2 points for not being able to get further on the integral. But now let's solve the integral. First we can simplify the integrand. I would take 2 pi times 2 to combine to a 4 pi. Definite integral from 0 to 8 of, this is a bit of a mess. I have 4, maybe let's go with x to the power of -1/3, just promoting this to the numerator, times 4 minus x to the power of 2/3 to the power of 3/2 dx. The reason I thought of putting this up into the numerator is I felt that maybe a u substitution is going to be the way to go on this. So we're about to find out. Any questions so far? Okay, so the problem says compute the area, exact surface area. Then there's somehow, some way this would resolve. And let's try by u substitution. U should be the inner function here, and I hope that the derivative of this is exactly this. And that looks like it might actually be the case. So I'll let u be 4 minus x to the power of 2/3. The differential du would then be 0 here minus 2/3. Subtract 3 over 3 to get the new exponent of -1/3 dx. And that's stuff we actually have in the problem. We do have x power -1/3 dx. So it seems like it's working. We can multiply by -3/2 in both sides of this equation to get x to the power -1/3 dx. So that would do the job on solving that integral. We can come back over here and say the definite integral is going to be 4 pi I'll multiply by -3/2. Then we have a definite integral from 0 to 8, and it's always your choice if you want to change the limits of integration now or later. Let's go for now, since sometimes that does simplify the work. If I plug in 0 into the formula for u, we would get a lower limit of 4. And if we plug in 8, then we would get 4 minus 8 to the power of 2/3. That is kind of nasty. And when I write the exams, I look for things like this and decide, maybe I don't want this on the actual exam and tone it down a bit. But this is still great practice. So we'll get 4. First you take the cube root of 8, so it'll be 2, which we would have to square. That would mean it's 4 minus 4, which is 0. And if I thought about it, we kind of did that once over there, didn't we? So we have something that goes from 4 to 0, like that. And this is encouraging because we know the surface area should come out positive, and the limits of integration go from greatest to least. That does give us an extra negative sign, forcing this into a positive result. So that is helpful. Next, x to -1/3 dx combines to -3/2 du. So all he's missing is the du. And this 4 minus x to the power 2/3 is the variable u, which is raised to the power of 3/2. We're finally getting there, folks. Any questions to this step?
I got a question.
Yeah.
So how do you know when you need to change the integrating factor, or not the integrating factor, sorry, the limits of integration?
It's really pretty up to your choice. The times I would say definitely it's a great choice is if I'm doing a trigonometric substitution, because then you have many substitutions you might have to get through. And if you have to do substitutions multiple times, it becomes kind of tedious to undo every single substitution algebraically, and faster to just change the limits of integration. So my advice would be then, if you're just doing a u substitution and nothing else, I would just let it be your preference. If you're more comfortable changing the limits, I would do that every time. But if you're more comfortable undoing the substitution, I would do that every time as well. There's not necessarily a best way. Other questions about that so far? Okay, so let's resolve this integral, where first I'll divide 2 to get 2 pi times 3, so that would be 6 pi. Then we do have a negative sign here, and limits look a little bit odd, but a property of integrals say if you switch the order of integration, you negate the sign that's leading on that coefficient. So I'll call it a positive 6 pi and go from 0 to 4. It just looks a little bit better. And again, that is an optional step. We're taking the antiderivative of u to the power 3/2 on the next step. So this altogether becomes 6 pi. The power of u goes up by 1, so we get power 5/2, which we must multiply by the reciprocal of 2/5. And this quantity will be evaluated from 0 to 4. So that's where we're at so far. And now we have that 12 pi fifths multiplying, insert 4 here. We would be taking the root of 4 first, giving us a 2. Raise that to power 5 gives us 32 or something thereabout. But if you wrote 2 to the power 5/2 and just left it like that, I would consider that full credit, because the exponent law there is not necessarily the calculus. But it's just prettier to call it a 32, so I'll go with that. Then insert 0 would be minus 0. So this is our result. 12 pi times 32 fifths. Kind of a nasty problem because it was long and I don't want to take 12 times 32. So I would probably revise this problem so some of these things work out a little bit more nicely. But once again, if you left this as a 2 to the power of 5/2 and left this in this form, those would be appropriate stopping points for an exam situation. How do you folks feel about this one? It was long. I'd say that's the worst thing about it. For really, really long problems, the horrible thing about it is if I make a single mistake anywhere, the problem is essentially impossible to do. If I make a simplest mistake, I may not be able to solve this integral any longer. So one thing I'll leave as an open option on the exam is if you do have a mistake, or if you just simply get stuck, I'll give partial credit if you say, don't know how to proceed beyond, just approximate it using a Simpson's rule, and I would give some partial credit to that. Maybe not full credit, but say everything was correct here, and I got stuck. If you just approximate with Simpson's rule, I'll say with n is equal to 4, then I would give you maybe 8 out of 10 points. Oh no, yeah, how about 8 out of 10? That seems about appropriate. No, let's go with 9. 9 better. 9 would be better. Other questions so far about that one? Okay, so if you do get stuck, you can still do other things. If you get completely stuck, or if you just run out of time, explain how the process should go, and that would be for partial credit as well. Well, let's go on to the next one, unless there's any questions about this problem. Okay, so those are some of the longest problems that we could encounter on this exam. Already I'm a half hour in, so this would have to be sped up just a bit, or the problems would be a little bit shorter on the real exam, so they can be completed in an appropriate amount of time. Let's go off to section 8.3 next. In section 8.3, it says for us to find the centroid of the region in the xy plane bounded by the curves, which are y equals e to the x for curve 1, y equals 0, x equals 1, and x equals 3, where really only one of those things are curving. The rest of them are either vertical or horizontal lines. We'll still call them curves. So we want the centroid of that thing. So to do this, once again, a sketch is really, really helpful, and this would be provided on the real exam. So I first start by sketching e to the x when x is 1. When x is 1, we have height e, and when x is 3, we would have height e cubed. E is 2.7, so if we round to 3, e cubed is about 27. It's a little bit lower, but it's somewhere out there. I'll just put e cubed there. That's kind of cheating, but for a rough sketch, there it is. So at 3, we're at this height, and at 1, we're at this height. So it's a curve that would be increasing about like that. It starts to increase quite fast, so that should be the right inflection. And y equals 0 would be this line. Y equals 1 would be this line, or excuse me, x equals 1. And x equals 3, oh dear, hang on, would be this line. So the sketch would look about like that. So we have some thin plate or lamina, and we want to know where the center of mass is, or the centroid. To do that, we have to solve 3 integrals. On the real exam, I'm only going to ask you to solve 2, since 3 is a bit much. One integral is for the area. Another integral is going to be for x bar, and another for y bar. So you would have to solve the area integral in the exam, and I'll randomly select either x bar or y bar for the second one. You won't have to complete all 3. So be careful with instructions. You don't necessarily have to do everything on every problem, or else the exam would just be too long. So first, let's start with the area integral. I want the area under the curve y equals e to the x, as x goes from 1 to 3, and also above the x-axis. So it's an definite integral from 1 to 3 of e to the x dx, and these should go fairly quickly. Antiderivative of e to the x is itself. Just watch out for chain rule type stuff. If it was, say, e to the 2x, you'd have to counteract that by a half. We evaluate from 1 to 3, so this is e cubed minus e to the power 1, which would be just e. So now we have our area. Next things to do are x bar and y bar, and those would be the coordinates of the centroid. So let's just go down the line. First x bar, maybe we can solve it over here. By formula, the x-coordinate of the centroid is equal to the reciprocal of the area, multiplying the definite integral as we go from 1 to 3, of x times f of x dx. So that's what the formula would look like. And this is our y equals f of x. In other words, in the formula, f of x is e to the x. So we're going to do the definite integral of 1 to 3 x times e to the x dx, which would mean we do have to do integration by parts on this one. So let's set up our u. What should u be in this problem? We'd want to pick something that gets simpler when we differentiate it. So either x or e to the x. X is the good choice because the derivative of x just goes to a 1, which is less complicated than x itself. But the derivative of e to the x is itself, so there's no change. So if we let u be x, then du is 1 times dx, or just dx. We have to then let dv be e to the x dx. V is the antiderivative of both sides. Really, you're solving a differential equation when you solve this. It's separable even. And you would get e to the x. So if we plug all that together, we can say we have 1 over the area multiplying the result. So we do need brackets due to a distributive law. First we take u times v, so x e to the x, which will be evaluated from 1 to 3, minus the definite integral from 1 to 3, of v times du, which would be e to the x times dx. And that would be our result so far. But notice we've already solved the integral from 1 to 3 of e to the x dx. That was what we called the area. So this is all just the area in the problem, and we have 1 over the area multiplying. Let's do this evaluation next. So we can put 3, we get 3, e cubed. At the lower limit 1, we'd be subtracting 1 times e to the power 1, which would just be e. So that's the evaluation of that portion, minus the definite integral from 1 to 3 is the area that we said on the onset, and that's so far what x bar looks like. Then we distribute 1 over a into the result and go from there. But any questions first? Okay, so we could say, I guess there's a couple ways to do this, but this is attempting cancellation. I don't know if it's completely worthwhile, but you could say it's 3 e cubed minus e divided by a. Then here to here would be a minus 1 over a times a itself. So altogether, this is 3 e cubed minus e divided by a, which I forgot what that was, e cubed minus 3 minus 1, and that's a cubed down there. Then, because it's a timed exam, you can stop right at that stage. I mean, we can do a bunch of algebra to this possibly, but I would stop there and go off to the next thing. But any questions to that step? Okay, then let's do y bar. Again, on the exam, I'm only going to pick either x bar or y bar, but it'll be selected randomly, so we might as well do them both for the sake of practice. And let's next write down the formula for y bar. So by formula, y bar is equal to the reciprocal of the area like before, still the definite integral from 1 to 3, but this time we take a half times the function f of x squared dx. But f of x is still e to the x, so this squared would just be e to the 2x altogether. So we could say that y bar is 1 over area times, we can, if we like, pull out the half to get 1/2. The definite integral from 1 to 3, if there's e to the x there, then e to the x squared is e to the 2x dx. And we need the antiderivative of that thing. So it's not too bad so far. This is 1 over twice the area, multiplying. We take the antiderivative of e to the 2x, which is itself. But now we have a chain rule situation in our check. So what's the missing factor to make this come out just right? A half would do the job, correct. So if we do a half, just check using the chain rule. The derivative of that quantity is exactly e to the 2x. Then we have to take the e to the 2x portion, evaluate it from 1 to 3. So that means we have 1 over 4a, multiplying the result of that evaluation. So first we input 3 to get e to the power 6, minus, throw in 1, and we have e squared. And that's all divided by 4a. And again, these probably do simplify, possibly in a very big way, but because it's a timed exam, I would encourage you to focus mainly on the calculus portions to demonstrate the understanding of that stuff, because that's where all the points are coming from. So if you stopped here by saying e6 e squared divided by 4 times a was e cubed minus e, oh, that must have been a typo right there, sorry, or just a bona fide mistake, e cubed minus e, then that would be a decent stopping point. But any questions with that so far? Okay, so that's the coordinates of the center of mass. What I would like to do, but is pretty much kind of impossible in an exam situation, is approximate the x bar quantity, the y bar quantity, and see if it looks like it's about maybe here for x bar. That's where I would put a steel rod to say balance the whole plate. If it was a vertical bar. A horizontal bar, there's more area down below here. So it should be somewhere along those lines. So if your evaluation gives you nice quantities, like say a third, a fifth, you'd be able to kind of check. But on an exam situation, it could be terrible stuff like that, so it might be hard to tell. Other questions with this so far? Okay, so that's 8.3. Again, these are problems that are really long, but this problem wasn't too terrible, it just had many steps. Yeah, question first?
On the x bar?
Yeah.
At the very end, is that still going to be times by 1 over area?
Oh, the 1 over area was multiplied first to this entire quantity, and so I just put an A under it itself.
Okay.
And then it multiplied way over to here, so it was really A over A. So I put just a -1. Other questions about that problem? Okay, let's go off to differential equations next. So we're in chapter 9, where there's just 3 sections we covered. 9.1 is kind of a tricky section because of the nature of the problems that you could see. A favorite problem for exams are, we'll just give you a differential equation, give you a function, and make you check whether that function is a solution. So let's do that for our 9.1 problem. Instructions will be something along these lines. Start by considering the differential equation 2y double prime minus y plus 3x cosine x is equal to 7 sine x. So we have a differential equation, and what you do not want to do is solve it. I mean, if you do know how to solve a second order differential equation with variable coefficients, then that would be okay to solve. But what we want to do is check if a particular function would solve it. So I'll grab something. Next it says determine if y equals x cosine x plus sine x is a solution. Okay, so for a problem like this that would be graded, it's graded in several parts. The first part that's part of the solution is you have to compute y prime. Let me make this a bullet so it doesn't look like a negative sign. So I'll first look for a y prime in your work. If this is our function, first y prime is going to be done by the product rule. So we'll take the derivative of the function x, which is 1, copy cosine x. Then we'll go plus, this time copy x, multiply by the derivative of cosine x, which is negative sine x. And I'll make this cosine x minus x sine x on a later step, but I always seem to forget to switch that right away. Then we add to it the derivative of sine x, which is cosine x. So first part of the problem is I'll look for the first derivative, but because it's a second order differential equation, for credit beyond this point, you must have the second derivative as well. So calculate for the next part, y double prime. Well, y double prime is going to be the derivative of all of this. Let me just make it look slightly prettier. It's cosine x minus x sine x plus a cosine x means we have 2 copies. So I'd rather take the derivative of the simplified version, much less work. We still have a product world that would occur right there. And I would probably bracket this out so I don't get mixed up on negative signs, since that negative sign would distribute to both of the terms. So first on y double prime, we'll have derivative of cosine, which is negative sine. So it'll be negative 2 times sine x. Then over here, we'll have the negative of, do this derivative with the product rule, will give us sine x for the first term, plus, then copy x, take the derivative of sine, which is cosine x, and that would be the second derivative. Again, we have to work with these further, so the simplifications you do turn out to be really helpful. So here we can say this is negative 2 sine x, distribute the negative, we'll be taking away sine x again, minus x cosine x. Oh dear, I think it's, yeah, I made it, just barely. So then that simplifies to negative 3 sine x minus x cosine x. So that's the situation so far. Now we're ready to go back to the differential equation. Any questions so far? Okay, so if the differential equation just has y prime, you would only need the first derivative. If it has y triple prime, you would need up to the third derivative in the process. And the next portion that we'll be looking for is, we're just going to do some substitutions. So I'll look at the left-hand side purely, which goes 2y double prime minus y plus 3x cosine x. All we need to do is substitute in the result we had for y double prime, and we were already given the result for y. So we'll throw that into this left-hand side to get twice y double prime is negative 3 sine x minus x cosine x. Then we take negative of y, which means we go all the way up over here. Opposite of a y would be negative x cosine x plus the sine of x. Then I'm just going to copy 3x cosine x. So plus 3x cosine x. So all I'm looking at so far is purely the left side of that differential equation. We're going to simplify all of this algebraically. If we hit 7 sine x, we found a solution. Or rather, we were given a solution. If our result is anything other than 7 sine x, then this would be a non-solution. So let's continue further. Any questions to this step? Okay, so next up, we have that this would be equal to, let's call this negative 6 sine x minus 2x cosine x. Distribute the negative, and we'll get negative x cosine x minus sine x plus 3x cosine x. And we can skip a bunch of steps here, but if it's an exam situation, then these are really high stakes distributions, so careful is probably preferable. But now let's look at our like terms. From here to here, we get to negative 7 sine x, then negative 2x cosine x plus 3x cosine x. Well, really all of these combined. This will be negative 3x cosine x altogether plus 3x cosine x, which implies a cancellation. So we did hit, miraculously, negative 7 sine x due to these three terms canceling out. Then there's one last thing for full credit. What would be the final thing we have to add here for the entire solution? Sorry, say again? Not quite.
That it's not a solution, right?
Close. Oh yeah, correct. It's not a solution. I was happy with the 7 sine x. But good idea, it's supposed to be positive 7 sine x. So the very final thing you have to add for full credit is you have to state the conclusion. The conclusion is that y equals x cosine x, or let's just say this, in context this must have been the thing in question, is not a solution. So don't forget to add the conclusion at the very final step, since I need to know that you know whether it's a solution or a non-solution at the very end. Yeah?
Do we have to write it, or can we just write cosine x does not equal 7 sine x, just the symbol does not equal?
Well, if you did say that, it still would be a question, if it's not equal, does that mean it's a solution or a non-solution? So still you'd want to say, you could abbreviate and just say solution for a very abridged version or non-solution for a very abridged version. Does that make sense? Cool. So that would be the total 4 parts that I'm looking for in this, where the first derivative, second derivative, and if further necessary, would be given probably equal weight. Then this is probably going to be most of the work, checking if this comes out, or simplifying this result, and maybe 2 points out of 10 to give a conclusion. State whether it's a solution or a non-solution, and then that's the full problem. But other questions about 9.1? Okay, so in sections 9.3, 9.5, we were not checking solutions, but we were producing them in very specific situations, the separable equations and the linear, first order. So let's go to those next. Unless there's any questions folks would like to discuss first. Okay, so now we're off to section 9.3. And I lost my problems. Oh, here they are. So in 9.3, this one says to solve the initial value problem. And the initial value problem we're looking at on this one is y prime equals x e to the negative y squared with the initial value that y at 0 is negative 2. So that's what we're going to solve on this one. And in 9.3, it is a separable equation, but we can tell it's separable mainly because we don't have a plus between these terms. If it was, say, y prime plus y, we can consider this a first order linear equation. But in this format, the best we're going to hope for is that it's separable. And if you do want to solve a separable equation, the very first step I would use is convert to Leibniz notation. Well, we're going to call this y dy dx equals x e to the negative y squared. So in this version, y prime is really referring to the derivative. In this version, when we write dy dx, it depends on the context. We can consider it to be a differential, where dy and dx are different variables in their own right. That means we can separate things in terms of x on one side, in terms of y on the other. I would start maybe by first, how about we multiply both sides by dx, so that y dy is x e to the negative y squared dx. So we have dy dx on opposite sides. The next problem is, well, where would be the next problem on this equation?
Dividing the e negative y squared.
Multiply both sides.
Yeah, we need to get rid of this because it depends on variable y. So either divide this on both sides or multiply by itself with a positive exponent. So we can go like this on the next step. E to the power y squared causes a cancellation here, and we'll throw it in that step there. And let me carry this up to a new column. This then converts to, let's call it, say, y e to the y squared dy equals x dx. Once we're satisfied that we have all variables that are necessary on one side and the other type of variables on the opposite side, then we've separated the equation entirely, and our next step is to take the antiderivatives of both sides with respect to variable y on the left, with respect to variable x on the right. So that's always our immediate next step. Then solving this one could be terrible if it looks like this. We would have to use the fundamental theorem of calculus part 1. That's possibly not appropriate for an exam. But if it's this, now your u substitution is on the table that we can get through. So we'll solve the left-hand side by saying u should be equal to this function because the derivative of it involves y. So if u is y squared, then du would be 2y dy, and so 1/2 of du is y dy. So the y dy are these quantities. We'll replace it with a half du and e to the u. Any questions with that setup so far? Okay, so the substitution on the left gives us 1/2, the antiderivative, y dy has been replaced with a half du. It'll be e to the power of y squared, but that is something we named as u itself. So the left-hand side is about ready to go. The right-hand side is terrific, antiderivative of x dx. I'll do it on the next step. It just seems like a nice thing to do. Let's do both antiderivatives at once. We get 1/2 e to the u on the left equals x squared over 2 plus a constant of integration on the right. So that's where that step takes us. Does that look all right to folks so far? Okay, so on these separable equations and on the first order linear equations, or rather just on the separable equations, it may be a situation where we have to leave the problem in implicit form. If that ever comes up, that would be written in the instructions itself. It would say, once you solve it, leave your answer in implicit form. But for all other situations, we would be expected to solve for the variable y in this case. So let's continue on by, say, maybe undo the substitution as the very next step. We have 1/2 e to the y squared equals x squared divided by 2 plus a constant. Now we have two routes that we can take. We can either solve for the variable first, the variable y, or we can use the initial value to solve for the constant. It really is up to your preference, but sometimes solving for the constant first is less work. So let's go with that route. Any questions first?
So that right there is the implicit part?
That'd be implicit, yeah.
Okay.
As soon as you get to y equals something, whatever it comes out as, this would be the explicit solution. Implicit means we think there's a function here, but we're not sure what it is until we solve for it. What other questions so far? Okay, so let's solve for the constant c using the initial condition. The initial condition is telling us that when x is equal to 0, the dependent y variable is equal to -2. So we can input those results down on this line. So -2 goes in place of y, producing 1/2 e to the power of -2 squared equals, we're inserting 0 on the left, or excuse me, right-hand side. So this would be a 0 plus a constant. So the constant c is just this entire value on the left, which is 1/2 e to the power 4. So that's our constant of integration, c. So we can come back over here and say that this converts to 1/2 e to the y squared equals x squared divided by 2 plus 1/2 e to the power of 4. So we're on our way. Our next task will be to solve for the variable y. So to do that, probably first, I wouldn't use a natural log immediately. We could, but it is extra work. I would first say multiply all sides of the equation by 2 to get rid of this 1/2 that's in every single term. So if we do that, we get e to the y squared is equal to x squared plus e to the power 4. What would you say the next step should be then? Actually, you could do that at this step, since if you took the square root, it'd be y squared itself multiplied by a power of 1/2. Or, hang on, would that be okay? That could possibly be a problem, because then we would have the exponential function e wrapped inside the root. So we would have a problem getting rid of base e. Yeah, so we'll do the natural log first and then the square root, like you said. So if we take natural log of both sides, now we're looking at natural log of e to the y squared equals the natural log of x squared plus e to the power 4. So the natural log has caused this cancellation. Now we're just doing with the y squared. So in the very next step, I feel like we ought to go to a new column, is that y squared is the natural log of the input on the right-hand side. So this is altogether, this is a lot of arrows for one problem, but now we're on y squared is natural log x squared plus e to the power 4, and we'll take the square root of both sides. But if we take the square root of both sides, y would then become positive or negative the square root of natural log of x squared plus e to the power 4. What we do have to do still is resolve which value should it be, positive or negative. But there is a major trick to that. Anyone see the trick on picking the correct sign?
The original value given?
Exactly, yeah. So an initial value, if you're given a negative, then that should be the value of the root. But you could also check it out. If I put 0 here, I'd be getting a 0 there. It'd be a natural log of e power 4. So that'd be plus or minus the root of natural log. That wiped out to 0 e power 4. But then there's a cancellation again, and this becomes plus or minus the root of 4, which is plus or minus 2. But remember, we should have a negative 2 like you said. So you can bypass this and say, as a shortcut, the root should be negative so that we get the negative 2 from the initial value. So the result is y equals negative natural log x squared plus e to the power 4. And that's finally our solution to that differential equation. Any questions about that so far?
I guess I got a question.
Yeah.
So if you did, like, can you separate the natural log? So if you do, like, natural log of x squared plus natural log of e to the 4th and then cancel the e to the 4th, and that would be okay?
Sadly,
Or
we
no?
can't.
Okay.
Yeah, the trouble with that is there's really only two great formulas for this left-hand side. They go a times b would be, like you said, natural log of a plus the natural log of b, or it could be in a different problem, natural log of a divided by b, which is just the same but with a negative sign. But sadly, just like with square roots and other things, there's no formula for a negative right there. In fact, that's a huge problem because a really interesting question you might have is, if you want to take x minus 1 cubed, you just FOIL it out a whole bunch of times, right? And there's no problem. But if you take x minus 1 to the power 1/3, there's no straightforward method for that. Until we get to chapter 11, the binomial series, the result of all this stuff with sequences and series can give us a formula for that thing. So we'll figure out how to essentially FOIL or multiply things with fractional powers. But a punchline, or a quick short answer to that is, pluses or minuses inside the function tend to mess things up, sadly. Other questions about that? Okay, let's go off to 9.5, where we have 7 minutes, so we may not get to the very last problems. But if people are curious, I could scan this and upload it, so you could take a look at what those were. Does that sound like a valuable thing? Okay, so there'll be an extra file, so if you're curious what these were, I'll upload this as well. So the last one that we may get to today is section 9.5, where we're solving first order linear differential equations. And this problem says, simply find the general solution to the differential equation, which is e to the xy prime equals 1 plus 2 e to the x times y. So that's our differential equation. One thing I should mention is when I write the exam, I'm going to pick on random whether this one is an initial value problem or the previous one. So you should expect something to randomly happen, but it'll be one or the other. So now the next thing I would like to do is, if I'm going to solve a problem like a 9.5, let me just pull up some of the notes to be quick about what we need. We're going for this format for a y prime, a function times y equals some other function q. So the first thing I want to do for this is rearrange it to that format. So I do have a y prime here. Sure, there's an e to the x, but we'll deal with that later. Subtract 2 e to the x times y, and we'll just get a 1 on the right-hand side. So it's beginning to match the format of y prime times a function equals some other function, which is constant. Next thing we should do, just because there can possibly be a shortcut, again, this will be decided by a random number generator for total fairness, is I would take this right here and compare down there. So the comparison is the derivative of e to the x equals e to the x. If this matches, that means we can completely skip the integrating factor. Sadly, the derivative of e to the x is not negative 2 e to the x, which means the very next step we have to do is the integrating factor I of x. Well, before we get to that step, we still have to get to this format here, which means just before we get to the integrating factor, we must divide by e to the x. So that's our real next step. Questions first? Let's get more chalk. So let's take e to the x, divide it on all sides of the equation. The result would then be just a y prime divided by e to the x here. We'll have a minus 2y. Divide by e to the x here, and it's 1 over e to the x. I'll call it e negative x. So that's where we're at so far. That implies that we have a certain function p of x in the formula above. So this says p of x is equal to, what would be our p of x function? Yeah, so we take whatever the coefficient is here, provided that's a coefficient of 1, so negative 2. Then the integrating factor, I of x, is e to the power of the antiderivative of p of x, which is negative 2 dx. But that would be e to the power of negative 2x in the antiderivative. And in this context, we always pick the simplest one. So it'd be e to the power of negative 2x. We take e to the power of negative 2x, and we go back over here, multiply all sides of the equation by that quantity. So we would have e to the power of negative 2x times y prime minus 2 e to the power of negative 2x times y equals e negative x times e to the negative 2x, which would combine to e to the power of negative 3x in the next step. So we took something that looked kind of nice, we made it way worse, but we had to, because now this is the result of some kind of product rule. But once again, let's run this check, because this check tells us whether we did everything correctly. So I need to take this function, e to the negative 2x, compare it with negative 2 e to the negative 2x. Once again, the comparison is by d dx of e to the negative 2x. The derivative would be e negative 2x, multiplied by the derivative of negative 2x, which is negative 2. So that's precisely what we have here, which means things are going according to plan. So let's go on to the next step. Any questions so far? Okay, what I'm going to write is a skippable step, and that step is that if you take e to the negative 2x, multiply it by y, and take the derivative, you should check out, just by inspection, the product rule would give you precisely all this stuff. You could say, take the derivative of y, there it is, y prime, I still don't know what y is, copy e to the negative 2x, over here copy y, and put in the derivative of e to the negative 2x, which we verified does come out correct. That's now equal to e to the negative 3x, and this is the step where we would take the antiderivative of both sides at once with respect to the variable x. So we're at this stage so far. But on the left-hand side, the antiderivative of a derivative is really just the value e negative 2x times y. You don't have to necessarily write that times. And here to here is an okay step to skip if you like. Then the right-hand side is e to the power of negative 3x. We multiply by negative 1/3 to make this come out corrected with a chain rule, and add the constant of integration immediately. So that's where we'd be at this stage. And what's really cool about 9.5 problems, all of them could always be put in explicit form. 9.3, it kind of depends, and the instructions will indicate which form you need. If it says nothing, you can solve for y. If it says leave it in implicit form, you would have stopped right here. But 9.5, we just divide by e to the negative 2x. And you can write this in a lot of formats, but if you're like me right now and running out of time, this would be completely acceptable. So that's the solution to the differential equation. Any questions about it? Or if you want a fancier answer, you could say multiply by e to the power of positive 2x, y would be equal to negative 1/3, e to the power of negative x plus e to the power of negative 2x times a constant, and that would also be a fine format for the answer on that one. But that's how the first order linear equations would go. Any questions so far, folks? Okay, so this looks like it may be a decent stopping point. So for the last problems, I have a couple problems on finding the convergence divergence of sequences like we did, and determining the convergence divergence of series. But since we're pretty short on time, I'll scan this and upload the answers as soon as possible.